I thought of explaining the reactive system conceptually before I get to the example part, which is what I will do in this video. We have three methods: atomic, molecular species, and extent of reaction. Using my final year project, I will prove to you that even if you have a book example or a real life case example, you can still apply these three methods to find what comes and leaves out of the reactor. In the final year project, I had two reactors. One was called the Alkylator and the other was called TransAlkylator. They were both necessary to convert petrochemicals like ethylene and benzene to another important petrochemical, which is ethyl benzene. This production of ethyl benzene will allow us to produce what we call styrene, and then by polymerization process you will have polystyrene. It is a very important product that is used in home and appliance installations. The reason we had two reactors is the fact that when you react ethylene with benzene, it will form ethyl benzene, which is what we want. But it will be then consumed to produce an undesired product, the product that we don't want, which is the diethyl benzene. So if you have another reactor, which is the TransAlkylator, it will transform the diethyl benzene to make double the amount of ethyl benzene, which is what we want. And before and after these reactors, we had a physical system, the system that does not have reactive system, such as the one that I showed you before when I did material balance for the physical system, the two distillation columns and the splitter point and the mixing point. Coming back to the reactors, we had the TransAlkylator, and because it receives only one reaction, we can use the conversion to calculate what comes and leaves out of the TransAlkylator reactor. After we finish the TransAlkylator material balance, I will move to the Alkylator material balance, where it had two reactions, so we will not depend on conversion. Let's start with the easiest case, which is the TransAlkylator, since it had only one reaction. And as I always say, when we start with material balance problem, either for reactive system or non-reactive system, the physical system, we start with flowchart, labeling all the information, and then degrees of freedom analysis. Atomic species method does not depend on the reaction. Atoms cannot be generated and cannot be consumed. So what comes in terms of atoms to the reactor or to the physical system is the same as what leaves from the reactor or from the physical system. This is why I prefer atomic species. For the unknowns, we have the reactor effluent, and by effluent I mean what is exiting out of the reactor. For the benzene, ethyl benzene and diethyl benzene, we have the independent atomic species, only two, which is the carbon and the hydrogen. You need to make sure, as I said before, that the ratio of the inlet stream for the carbon and hydrogen in this case needs to be not equal, at least in one stream, as you see in the equation. And you can see it by eye, by the way, but I wanted to illustrate the method so that we are all convinced. For the relations, we have the conversion, which is 92.9 of diethyl benzene, the limiting reactant. And lastly, for the independent non-reactive species, we don't have any because we have no inerts, which are the nitrogen or the noble gases that are found in the 18th column of the periodic table. We will start with the fractional conversion equation. Inlet of diethyl benzene minus what leaves from the diethyl benzene, and this, by the way, is the portion that we call reacted, divided by the initial flow of the limiting reactant, diethyl benzene. This will give you 92.9, which is given already. We will manipulate the equation to find the flow of diethyl benzene leaving the reactor, and it should be less, much less, because the conversion is 92.9, it is 2.24 kilomole per hour. And yes, I said conversion because we only calculate what comes and leaves out of the limiting reactant. This applies to all the three methods, but you can't depend on conversion to calculate the other chemicals if you have more than one reaction. We will use it in the atomic balance for the carbon and for the hydrogen. We will have two unknowns and we will have two equations, independent equations, and we will simultaneously solve them together to find the flow of the ethyl benzene and the flow of the benzene leaving the reactor. For the extent of reaction method, we will need one extent of reaction, and as we said before, it is the term that considers the generation or the consumption. If it is the product, then we will have a positive stoichiometric coefficient, and if it is a reactant, then we will have a negative stoichiometric coefficient. This is the answer in terms of calculating benzene and the ethyl benzene that will leave the reactor. We already had the diethyl benzene that will leave, since we have already calculated the fractional conversion of diethyl benzene, the limiting reactant. For the alkylator case, we have two reactions, so we will have two exi. If you have infinite number of reactions, you will have infinite number of exis. For the alkylator using the extent of reaction or using the atomic species, it was assumed that the conversion of ethylene is 100%, so that no ethylene will leave out of the reactor, which will enable us to calculate the flow of the ethylene and the flow of the benzene entering the reactor. You will find the two exis first to calculate the flow of the ethylene and the flow of the benzene entering the reactor. And the same goes with the alkylator using the atomic species. We had already the ethylene conversion 100% the same, so no ethylene will leave the reactor. I will repeat myself, and we will not need exi anymore because atomic species considers what comes in terms of atoms and what leaves in terms of atoms. So we will end up having two equations with two unknowns, and the unknowns are, in this case, ethylene and the benzene. Solve them simultaneously and then you will find the answer. Now that we solved the reactive system, I want to give you some of the important tips. The first step is to use the extent of reaction when you have an equilibrium reaction, because it will give you fast results. If you have a single reaction, then you can use molecular species because it will calculate everything fast using the conversion. If you have multiple reactions, then you can use atomic species because it depends on the atom. You will not consider the reaction, what comes and leaves, the generation and the consumption. You will just consider the atoms that came and left out of the reactor. I saved complicated problems that I will discuss in the next video that will show you the strength of each method in each case. Stay tuned to that video.